Oh, and welcome to my presentation about the power of compressed air. My name is Daniel, and I'm going to do my best to walk you through our experimental process and the wealth of knowledge I have amassed in the past few sleepless nights. We set off to measure the potential energy stored within air after it was compressed. I thought there must have been some way to quantify a value like this, like mgh, or 1/2 CV squared. The results? Arguably more exciting than either one of those, depending on your relationship with calculus. Without further ado, let's jump into it. First, a quick word about gauges. Gauges have a peculiar way of measuring pressure. When they read 0, they are really picking up 1 atmosphere's worth of whatever unit that they are in. It could be bar or PSI, KPA, whatever you want. But they start off at 1 atmosphere. That's their 0 mark. So keep that in mind. It'll be important a bit later on. You remember chemistry, right? In chemistry, we have a little law called the ideal gas law. It relates pressure P, volume V, moles N, which is the stuff in a given area, R, which is a constant, and the temperature of the gas T. If you've taken chemistry, you're likely familiar with some of the applications of a law like this, but have you ever wondered what it really means? I mean, what even is pressure times volume? For the time being, we're going to ignore that NRT stuff. What we really care about is pressure and volume. As we know, pressure is equal to a force exerted over an area, taking the dimensions of F over x squared. Volume takes the dimensions x cubed. When you multiply them out, you're left with F times x, which we've all seen. That's work. This means that one completely valid and perhaps even intuitive way of interpreting Pivnert is through the lens of conservation of energy. Energy initial is equal to energy final. You have a certain amount of energy in your gas, and at the end, you're going to have that same amount of energy. So in other words, pressure times volume equals work. Kind of. It's a little more nuanced than just that. To demonstrate, here's a container of gas. These particles are all bouncing around at unimaginable speeds, applying pressure and exerting a force on the walls of the container. So what do you think would happen if we raised our temperature? Well, since we're holding our volume fixed, Pivnert tells us that an increase in temperature results in an increase in pressure. But is any work being done? No. Work requires movement. It requires change of some kind. Only increasing pressure is like pushing against a wall with ever-increasing force, but never actually going anywhere. Is it tiring? Sure. But is any work being done? Not in the physical sense. And likewise, with pressure, it's not enough for just the pressure to go up for work to be done. Something else has got to change, and that something is volume. Just like pushing a door to open it is doing work, compressing air so that its volume change is doing work. So our actual formula is P times delta V equals work. We need that change in volume for work to really be done. Hold on a second though. Did you notice how the pressure changed as the air was compressed? It got larger. The force acting on each wall of the container got larger. Whenever you have something changing with respect to something else, it often spells impending calculus. That means our actual formula is P times dV. Integrating that to solve for work yields this equation. The integral of P dV equals work. So is that it? Are we finally done? Well, there's actually one more thing missing. A negative sign. I know, a negative sign always has to show up to ruin the day, just when we were beginning to understand something. I think explaining this geometrically will help to clear things up. So here's the equation again. The increment of our integral is dV, which means that volume is our independent variable. P, pressure, is a function of V. Together, we can get a pretty good graph out of this. Our only issue is we don't know what f of v is. To fix that, we have to look to a constituent law of Pivnert, Boyle's law. Here it is. P1v1 equals P2v2. Let's call these ones variables. After a touch of finagling and moving things around, gonna put f of v in front of here, we see it's a 1 over v graph. So why do we need a negative sign? Think back to the chamber and piston. When we compressed it, we reduced its volume and stored potential energy in the gas. That potential energy is positive. The gas did negative work by opposing the piston's compressive force, but we did positive work because our force was in the direction of the motion of the piston. Since the volume decreases, we take the integral from right to left. If you take any integral from right to left, you get a negative answer. We want a positive answer in this case because we know we did positive work. That is the reason we have to have that extra negative sign, because everything's from the perspective of the observer and of potential energy. Pause and ponder that for a second, because it's really important that you have a firm grasp on the intuition of that extra negative sign. Final bit of theory. Those of you who like calculus, you're going to like this. Here's our integral. It's got a negative sign, it's got all of that. We need some bounds, so why not v1, which is a vi, and a v2, which is a vf? It can expand or compress. It can expand or compress. It works either way. Remember that formula we had? P equals P1 v1 over v. Let's plug that into this integral. Since P1 and V1 are constants, we don't have to worry about them. Pretend like they're outside of the integral if you have to. The integral of 1 over V dV is natural log of the absolute value of V, evaluated from V1 to V2. So now we're just going to do a lot of log rules and simplification. Expansion. Flipping those guys around. Log division. And there it is, our golden formula. Okay, so now that we derived a formula for the work done by compressing or expanding air, let's try it on that piston problem. Say it has an initial volume of 5 liters and an initial pressure of 1 atmosphere. We compress it, and after doing so, It has a volume of 1 liter and a pressure of 5 atmospheres. And of course, here's our shiny, amazing theoretical formula. So step 1 is to convert all of these units into the SI MKS system. So I will do so right now. Next, we just plug in and solve. So it turns out our P2, our PF here, is an extraneous piece of data, but it won't always be like that. More on that soon. After computing this, we see that we theoretically stored 815.2 joules of potential energy in the piston and chamber. So this here was our main experiment. The idea was to pressurize a rigid container of some kind incrementally, open a valve, and convert the potential energy we had stored into mechanical energy that we could measure. We'd open the nozzle all the way, spin a turbine with a weight attached, and calculate omega so as to also include rotational kinetic energy. First, I tried with a mason jar, but those don't sit well being pressurized. It leaked all over the place no matter how much caulk or Teflon tape I put. Praise be to Goody, who came to the rescue with a soda bottle he had jerry-rigged with a stick up its, a valve on the bottom. We fitted a nozzle through the cap and thus were able to expel air like a demented super soaker. But oh boy was it fun. On the left lies the bottle we actually used for the experiment. Note the peculiar valve in its ass. On the left lies the bottle we actually used for the experiment. Note the peculiar valve in its ass. Without that airtight entry point, this would not have been possible. In the middle of the screen is the best picture I have of that failed mason jar. I tried countless times to seal it, but every time it would leak out of the top or out of the bottom. On the right sits a really nifty contraption, our nozzle. We drilled a hole in the soda bottle's cap a bit smaller than the nozzle itself. This would allow for another airtight seal, supplemented by an O-ring and a nut. This thing easily got up to 100 psi when Dean messed with it. Here's some pictures of the actual experiment. I had to get 2 chairs to stand firmly on that flimsy red table, then construct a cardboard and coat hanger socket to hold the turbine. It wasn't hard, but it did piss my mom off, tearing my house apart. So here's a video of a trial run at 50 psi. That thing spins fast. It's hard to even count how many times it goes around, even in slow motion. That's good. Before we get into the experimental stuff, I want to discuss theoretical calculations. Unlike a container and a piston, where we know the initial volume and we know what we compress it to, we have a bottle. Instead of compressing air we already have in the bottle, we are pulling air out of the atmosphere and pumping that into the bottle. These are not so different, though. Let's call the volume of air moving into the bottle V outside, and the volume of air already in the bottle V inside. Can you see the similarity yet? When we pump air into the bottle, we are compressing all of the air, V outside and V inside. All of the molecules in V inside are going to be compressed just as much as the molecules in V outside. Hell, we might as well combine them and call it V1. So all we have to do is solve to get V1. Then our golden formula should work perfectly. This is where we have to take into account gauge pressure. and use that previously extraneous P2 to work backwards. I'll show you how to do one of these calculations and skip ahead after that. So we have to add 1 atmosphere to the reading of the gauge. So that's what we're going to do. So if a gauge reads 10 psi, it really has 24.7 psi. So now we have to convert that into Pascal and work backwards to solve for V1 using Boyle's law. So we're going to solve to get V1, and V1 is equal to 0.0336 meters cubed. Now we can plug that into our equation here and get an answer for how much work we theoretically pumped into the bottle. And our answer is 176.7 joules. If we do this with every increment, this is what our table is going to look like. This is assuming absolutely no waste heat or error. My experimental data is going to look very different. So here's the moment where we've all been waiting for, the raw data. I want you to notice how the weight I put at the end of the string had to be increased each increment, or almost every increment, because I kept running out of string. So now we're going to calculate a bunch of values out of that. I didn't want to sit and do 80 computations on my own, so I wrote a Python script that would do it all for me. These are the results. So now we're going to average the three trials for each increment and plot that on a graph. So here's our data. You can see the theoretical graph definitely has a little bit of a curve to it, though it's not as pronounced as the experimental graph. I think the percent error versus pressure graph can shed some light on that. As we increased the pressure in the bottle, not only did we theoretically store more energy, but we also improved our efficiency. Higher forces, higher omegas, steadier airflow, all of which probably reduced the significance of the waste heat and most likely contributed to that curvier shape.